this is a quick introduction to implicit differentiation and why it might be used and how to actually use it. So what you'll find is that there's some functions which are actually very hard to put y on one side of the equation and x on the other side of the equation. So an example is this equation here. It would be very hard to do that, and sometimes it's actually impossible to separate your y's and your x's. So in implicit differentiation, we take the whole equation and derive it with respect to x. So let's start off with an easier example and show you how that's done. So x squared plus 3y squared equals to 4. And we're taking this derivative of x. So let's start off with the x squared term here. So the derivative of x squared is simply 2x, and I'm sure you know how to do that. And the derivative of our constant here is just going to be 0, because the derivative of a constant is 0. But the tricky part comes with this 3y squared over here. So let's break that down a bit. When we take the derivative of y with respect to x, we need to remember that y is actually a function of x in this case, because we're taking the derivative with respect to x. So in this case, we're going to have to use the chain rule, which is over here. So what is our f prime, which is the outer function? Well, the outer function is simply the square term at the top, and the inner function is just y. So let's start off with this part first. So the derivative of the outer function, we just take our 2 down and times it by the constant, and 2 times 3 is 6. Now the inner function just stays the same, so it's just 6y. Now, g prime over here, that is the last bit, which is the derivative of y. Now we have to be careful with this, because remember, we are differentiating this with respect to d over dx, which is the derivative of x. So when we do this, y is not going to be 1, it's going to be dy over dx, because y is a function of x and we're deriving it with respect to x. So we say dy over dx. So there it is, that is our derivative of 3y squared. So then let's put that back into our equation, what we've just found out. So then it's 2x plus 6y dy over dx equals to 0. Now for these equations, most of the time you'll have to rearrange for dy over dx, because that's what we're solving for. So take the 2x to the side, minus 2x, and divide it by 6y. And that is our equation. Now there's one more equation that we're going to go through so that we can learn the product rule, and this is a bit of a harder one. So the natural log of y plus x e to the power of y equals 2x. Let's start with the natural log of y first. So remember our chain rule, which is over here. So let's try that again. So we'll start off with this, which is the outer function, which is natural log. Then the inner function is y, and the derivative of y with respect to x is going to be dy over dx. So first, the outer function, once we derive a natural log, it's just 1 over y, which takes care of this part. And then we need to times it by dy over dx, because we're taking the derivative of y with respect to x. Our next term in the equation is this right here, which is where we need to use the product rule. So we're taking the derivative of x e to the power of y. Now in this case we actually have to use the product rule, which I will write down over here. So first of all, what is the derivative of this? Well, first of all, let's call f x, and we'll call g this part here. So the derivative of x, which is our f prime, so f equals to x and g equals to e to the power of y. F prime, if we're taking the derivative of x with respect to x, it is just 1. Now here's the tricky part. G prime, the derivative of e to the y with respect to x. We need to remember that we need to use our chain rule again. So let's just make a new line. And the chain rule I'll put up here. So how we're going to do this is we need to remember that for e to the power of y, y is the inner function, or so I'll just show you now. Y is the inner function, and the exponential is the outer function. So when we derive e, it's just going to be e, and the inner function of y stays the same. And then we need to remember for that last part here, we're taking the derivative of y with respect to x, which is going to be dy over dx. So that's what g prime equals to. And then we just use the product rule as we normally do. So we've got, I'll just move up a bit so you can still see the product rule, and I'll just write it down here. So you've got f prime, which is just 1, g, which is e to the y, plus f, which is x, and g prime, which is e to the y, dy over dx. So that's our, this right here is what the derivative of xe to the power of y is with respect to x. So this here is equal to this here. So that gives us 2 of our parts done. We've done this and this. And then the derivative of x over here is just going to be equal to 1. So if we put all of that together, which, sorry, you can't really see it, but I'll take everything down. So that means that we're going to have 1 over y times dy over dx plus e to the y plus x e to the y dy over dx. And then the derivative of x was just 1. And then, as usual, we just have to solve for dy over dx. So, how we can do that in this equation is we look at all the terms with dy over dx in it, and we move the rest to the other side. So in this case, the only term which we'll move is e to the y, and then we'll make dy over dx and factorize it. So dy over dx 1 over y, which comes from here, and then plus xey to the power of y, which comes from here, and that equals to 1 minus e to the power of y. Now the final step is we take this here and we move it underneath here, which means dy over dx 1 minus e to the y over 1 over y plus x e to the power of y. And that's our answer. And we just solved the implicit differentiation of ln y plus x e to the power of y equals x. So, yep. I hope you did enjoy the video. Please give me some tips, and if you have any questions, leave them in the comments below. Thank you.